Okay, today we have to talk about scatterplots and lines of regression. Now, where do these come in? These come in whenever we're talking about data. So this makes the scientist and me really happy that we actually get to start talking about data and what we do with it. We're talking in particular about two variable data, okay? So keep that in mind. We have two variable data. So the first example they gave in the book is they're talking about the number of visitors for each year. So year would be a variable. The number of visitors to the park, Yosemite National Park or something, would be the second variable, the second dependent variable, because the number of visitors depends on which year it is. The year does not depend on how many visitors there are. So make sure we have the independent and dependent in the right order. Let's talk about a scatter plot. Of course, you're going to have your x and your y-axis. You're always going to make sure you have labels on it, so maybe we'll put year down here. We'll start labeling things. 1992. This is going to get a little sloppy. 1996. Am I going up by 4? So now I'm going 2000, 2004, and so on. Okay? And I'll have a vertical axis that will be the number of visitors. And because that's a big number, I'm going to put it's going to be listed here in thousands. Okay? And let me make a few scale marks. Let's see, I want to go up maybe 5, 10, 15, 20, and so on. And let's just say I have some data points to put on here now. So let me go ahead and put some data points on here. So let's say the first year we had somewhere around 15,000. You put your little point. Let's see, there's 4 in here. 3, 4, 5, right. The next year it went up a little. Okay, I think I caught it that I hit the audio out, so I'm going to assume you didn't miss any audio. I'm just making up some ordered pairs. The next year I have to put the data point on here, put another data point on, put some data points on here, make a nice graph, okay? You guys are going to have a nice graph paper. I don't. Okay, so we do a little bit of plotting all these ordered pair points that come from the data. So, you know, your data would have come from a table, year, and number of visitors. Alright, so I took all those ordered pairs, I put them on here, and I say, I have a scatter plot. So now you know what a scatter plot looks like. You probably knew that already. I want to talk about correlation. Okay? So here's this word, correlation. Correlation describes how the two variables are related, and the graph is just a nice way to show this, okay? It shows that there actually is a trend here. As the year gets higher, the number of visitors appears to be going down. So what you want to do is you want to look at this with your eyeballs and draw what you think would be a line of fit through this data, okay? So there's something I might have missed a little bit, might have changed it, but okay. That's my first try to line a fit through the data. And I look at this and I say, well, it's going down, so what we can say is this is a negative correlation, okay, because the slope is negative. Okay, and that is just a slope thing, okay? So correlations can be negative, positive, or none. So I'll have to show you some examples of that. The other thing you tell me with a correlation is it could be weak or strong. So if there is a correlation, negative or positive, is it a weak or strong correlation? And that's simply describing how tightly clustered the data is around the line. And again, it's a judgment call, but I might look at this one and say, It's kind of funny. Yeah, boy, strong or weak. It's kind of medium. What do you think? Take your judgment and see what you think. We're going to want to quantify this a little later on, so I'm going to go with a little bit strong. Okay, so let's take some other examples. Okay, this time let's say I had a graph. It looks like this, a scatter plot, I should say. It's the number of cell phones for a given year. I'm missing a little bit of my axis, but forgive me. We'll describe this correlation though. So we're going to describe the correlation, and the question would be, first of all, is it positive or negative or none? And I would say, well, as I look at this, that appears to be a pretty good line through the data. That is a positive slope, so I will say the correlation is positive. And then I'll say, and those points really do fall close to the line, so I'm going to say it's a strong. So it's a positive, strong correlation. Okay, let me draw another one. Here's a graph I've drawn real quick. It shows independent variable would be the last digit of your phone number, and a dependent variable might be how many dogs you own. So say your phone number ended in a 1 and you had 2 dogs. You know, your phone number ended in a 3 and you have 4 dogs. You know, that kind of thing. So you look at this and you just look at that and say, wow, I don't see a trend. I can't say if it's going up, it's going down. I can't see any trend at all. So I'm going to look at this one and I'm going to say no correlation. Okay. Now there's one other example I want to give here. And this one's going to show the year versus the number of senators in our U.S. Senate, and as you know, that's always 50. So when you look at this, you've got this horizontal flat line, and you can say, yeah, there's a line of best fit. Oops, let me get my pencil. There certainly is a line of fit here, but there's no correlation because the slope is 0. So that's another way you can get no correlation. Alright, let's look at how we're going to do these lines of fit and get our prediction equations. Okay, so I'm a little confused with what actually got recorded here. I have my data, the year since 2000, and the average number of cell phones per household, okay? I took my red line and I drew what I thought looked like a good line of fit, okay? So that red line is my line of fit. It's got a little bit below, a little bit above, and pretty closely approximates my data. That line does. So now I want to find this prediction line, or prediction equation, okay? So I need the equation of the line, that red line that just I drew as a line of fit. So I'm going to pick 2 points on my red line, and I picked those 2 points here with blue. So it looks like I have this first point here, 1, 2, 3, 4, comma, 3, and this other point I have 1.5 comma 1.5. Okay, so my prediction equation is this red line. I found 2 points on that line, and I can find the equation of the line through those 2 points, and that will be my prediction equation. So let me do that real quick. Okay, that's a little freaky. I came out with 0.6x plus 0.6 as my line equation of a line for that prediction. Yeah, that came up funny, but you can see my work over here. Maybe you can find a mistake, but that's what I got, so I'm going to go with this. It should be no reason why it's wrong, it's just funny. And this is a prediction equation, because what I can do is I can make predictions now. So let's say I want to predict, I've only got the data for years 1 through 5. Maybe I want to predict when, you know, it's 2007, okay? So let's make a prediction when x is equal to 7. So that'll be the year 2007. So in the year 2007, the average number of cell phones per household we might expect to be 0.6 times 7 plus 0.6, and that number comes out to be 4.8. You might expect 4.8 cell phones per household on average in the year 2007. Now, let me make one quick statement about just the validity of making predictions, okay? When you're making a prediction, like we just did, that's outside the data, okay? So we made a prediction, make a new color here. We made a prediction that was 2007. So we even went extra far, and we did that, kind of extended the line, and we said, aha, that will be the answer right there in 2007. That's great, but it's a little bit worrisome because you're not sure the trend will continue. Okay, it's possible you could have looked at this, and what actually comes to pass is the line comes up, and then maybe it starts to flatten out. You know, because honestly, you don't have more than, you know, that many members in a family. So why would you have more and more cell phones per family? So I can imagine that trend's going to slow down. So that's a little bit dangerous to go outside your data set. Okay, so here's a summary for that. When you make a prediction outside the data set, that's called extrapolation. Okay, you're extrapolating the data, you're going outside the data set, and that can be dangerous. Okay, if you're not going outside, if you're staying within the data set, and you just want to find a value, you know, somewhere in between the values you already had, that we call it interpolation, and that's much more safe. It's usually a very good predictor. Okay, so far we had just, you know, kind of eyeballed what we thought would be a good line of fit. But now we want to start talking about what really is the line of best fit, okay? And we have some different words for this. We can call it a regression line. We can call it the least squares regression line. Those are all the same thing. And you're going to love this part about this because we're going to do this on a calculator. So you don't have to figure it out. It is calculator. It is possible, but we're going to do it on a calculator. The other thing the calculator spits out, they spit out this nice correlation coefficient. We talked about how things are correlated positive or negatively according to the slope. Okay, so R runs from -1 to a +1, whether or not it's a negative correlation or a positive correlation. R equals 0, there in the middle, of course, is no correlation. And R, if you looked at just the absolute value R equal 1, that would be a perfect correlation, where every data point perfectly lies on this line of fit. Okay? So if you get like an R is equal to -0.95, you're going to call that a strong, because it's close to 1, negative correlation. Okay, so I want you to take a correlation and describe it. R is equal to plus 0.45. How would you describe that? Well, if it were me, I would call this a positive but weak correlation. And how would you describe the correlation described with the coefficient 0.995. Again, it would be a positive, but a strong correlation. And if you looked at R is equal to negative 0.23, I would definitely call that one a negative and a weak correlation. Right. We can argue about the 0.45 value. There's no hard set rules about it. Let's bring that up for a discussion.